Hi, hello. Welcome to a Physionic study analysis. Today we're going to be going over a scientific review of over 145 studies looking at a particular aging phenomenon known as sarcopenia. This was a peripheral area of research for me during my undergraduate research and my master's research, going through my master's in exercise physiology. But that's not going to be the focus of this. We're going to be focused on what this scientific review has to illuminate for us. So we're going to also be relating it to mitochondria. So how do our mitochondria play a role in sarcopenia, which again is this age-related disease? If you're not familiar with who I am, my name is Nicholas Verhoeven. I'm a PhD candidate in molecular medicine, and I hold obviously my master's in exercise physiology, considering I was just talking about it. And I do these study analyses basically on a weekly basis. So go through a ton of data to end up at a conclusion. Now, of course, these are lengthy videos, so if you would like a more concise answer, while you're probably going to miss some of the context, you can skip over to the conclusions and takeaways section of this video. But if you're in for the ride and you want to know all the information there is to know about sarcopenia, what it is, what causes it, things of that nature, then let's get right into it, shall we? All right, so the topics that we're going to be covering are what is sarcopenia? Obviously, we have to cover that, otherwise we're going to be pretty confused throughout. What causes sarcopenia? So we're going to go through a bunch of different mechanisms of what's actually happening within your body. Obviously, the Physionic brand is based around physiology, so we actually have to understand everything related to the mechanisms, understanding the physiology itself, the pathophysiology. Then I'm going to briefly discuss, just to start to discuss how mitochondria are related to sarcopenia. And then for my insiders, if you're part of my Physionic insiders, you'll get access to the full version of this video and this analysis, which is also going to be discussing how mitochondria, so the mechanisms of how mitochondria contribute to sarcopenia. And I'll give you some information on how to combat sarcopenia as well. If you want access to this entire study analysis, including the insiders sections, then I'll have a ticker and a link so that you can join, and you'll get access to this as well as all my other full study analyses and a bunch of other benefits like seminars and office hours and things of that nature. So certainly hop on over there. Okay, but if you're just interested in these three topics right here, then let's go ahead and continue. And for the insiders, you'll get the additional two topics. So as I mentioned, the information is going to be gleaned from a scientific review of I suppose I shouldn't have said over 145. It is 145 studies long. However, we're not going to be going over any data specifically. We're just going to be looking at diagrams that I've put together. Okay, so I wanted to start out by looking at aging and muscle and the relationship between these two. So the way that the researchers have things defined here is that aging is having a noticeable effect on musculature if you see a 30% loss in muscle mass. However, they also define it as a 20% loss in cross-sectional area, or the width of the or thickness of the actual musculature. So here we've got our bone, here we've got the actual muscle mass itself, and then we've got a little bit of fat around marbling around the outside. But the overall distance from this point to this point, or diameter of the musculature, if we see a 20% loss, that is considered a prominent effect of aging in that scenario. Now, as we get older, if we get into our 70s and 80s, one of the problems, or one of the major problems, is that for women, there's an experience of 0.7% loss in musculature per year. So if you think that over a decade from that point on, you will have lost then 7% of your musculature. But of course, muscle starts to decrease far before the age of 75 or 70s, 80s years old. And for men, there's an even greater loss. So there's almost a 1% loss per year. So these are pretty significant numbers. I mean, to lose 10% of your muscle in a decade is pretty significant, especially if you've already lost a significant amount from the age of 50, 55 onwards. So there's a lot going on here. But what exactly is sarcopenia? Sarcopenia is, so we've discussed the loss of muscle mass and the loss of muscle cross-sectional area. We've looked at the percentage loss, but that's really just looking at the actual amount of musculature. The problem is, though, that it's not just defined by the actual amount of muscle, but it's actually more so, and I would strongly argue that it's more so defined by the functionality of the muscle. And this is an exaggerated example of functionality. Really what we're talking about is, for functionality, is can you get up from a seated position without using your hands or your arms to brace yourself to get up. Being able to go from a seated to standing position with just the power and strength of your legs. So it's really a relationship of that, exactly. So power and strength of your musculature. So I would say this is probably far more important than 70, 80% of the definition of sarcopenia, the loss of that power and that strength in the musculature. You could have really small muscles, but if they're functional, if they're efficient, then you do not have sarcopenia. So that's really the area that you should be focused on when you're thinking about sarcopenic loss in musculature, more so focusing on the functionality rather than the actual size of the musculature. Now, of course, those are tightly related to one another, so that's another factor. But overall, if anything, it's measures of functionality, so gait speed, sit to stand tests, things of that nature. So they're pretty simple tests, but they make a dramatic difference in terms of actually diagnosing sarcopenia. So what actually causes this? What causes this shrinking of the musculature, of the atrophying of the musculature, as well as a loss in that functionality of the muscles? So one of the chief reasons is, so if we have a single muscle belly, so we're looking at, let's say if we go back here, just a particular section of the arm, so just the bicep. If we were just to look at the bicep and then we were to zoom in and look at a muscle cell, so a single muscle cell, a muscle fiber, and then we were to zoom into that, so zoom into the muscle cell, we'd find that the muscle cell, the actual size of the musculature, but also the functionality of the musculature, is dictated by this balance of protein synthesis versus protein degradation. So your cells are filled with enzymes and functional proteins that actually serve, obviously, a function within the cell. And you need a certain amount of these functional proteins to have it be a functional muscle cell. And then if you multiply that out millions and millions of times over, then you have a muscle belly or a muscle structure that is functional and therefore can define if you have sarcopenia or not. So it's this balance of producing enough of these functional proteins while also getting rid of non-functional proteins, or proteins that have worn out their use. They've been damaged, whatever might happen. Ultimately, you have to have this turnover of synthesis and breakdown. So that's what creates that balance. When we're young, that's not a problem. You have sufficient synthesis and sufficient degradation or elimination of these proteins. However, as we age, this synthesis aspect starts to decrease and this degradation aspect starts to increase. So you can see that there's a problem there because you're not producing enough functional proteins and you're getting rid of a lot of those functional proteins, or getting rid of proteins in general. So this is one of the primary mechanisms that we see the shrinking of the musculature, but also effects on the functionality. Now, something else that happens is that the muscle becomes more anabolic resistant, meaning that it doesn't take up as many amino acids, which are the building blocks of proteins. And not only that, those amino acids then no longer have as much of an effect within the cell, and I'll explain that in the next slide. But another aspect is that they also take up less blood sugar. So this could be a huge contributor, obviously, to insulin resistance or a symptom of insulin resistance. So the muscle cell not only takes up less amino acids, it takes up less sugar, and it takes up less fat. I don't have that diagrammed here, but all three of the macronutrients that we use for energy and for many other functions within the body and within our cells are dampened, so that they end up being stuck outside of the cells when they should be shuttled into the cells. So why does that occur and why does that matter? Well, the amino acids that do end up finding themselves within the cells, what they normally do is they stimulate protein synthesis and they inhibit protein degradation. Not completely, but they at least sway everything towards protein synthesis. So clearly, as we discussed, one of the problems with sarcopenia and aging in general is that you have less protein synthesis and more protein degradation. So clearly, these amino acids, or having reduced levels of these amino acids, is at least one contributing factor for why we have this imbalance in an increase in protein degradation, which leads to the shrinking of the muscle cell. Now, in terms of the effects on fat intake or the uptake of fats for energy and for other functions, as well as the uptake of blood sugar into the cells, we have reduced levels of the expression of particular enzymes. These enzymes are crucial for metabolism, like glycolysis and beta oxidation, which are two metabolic pathways that take sugar and take fat and break them down into usable energy within the cells. So we see reduced levels of the production of these proteins, these enzymes, these functional proteins. So it goes a little bit back to this, so the lowered protein synthesis, but also less activation of the genes that encode the information for these proteins. So all of these, so across a wide variety of different areas, we see that aging and sarcopenia can have pretty drastic effects on the muscle cell. And this is only looking at a single muscle cell. So if you expand that out to millions of other muscle cells, there's a lot of issues. And to symbolize this, to show this a little bit more, is if we compare the muscle cross-section, so again, looking at the width. So if we were to cut a person's arm, not that this would actually happen, but if you were to cut a person's arm and then look down the length of the arm, you see that there's the bone here, you have the musculature here, and then you've got the fat that lines around the outside, so the subcutaneous fat. And you can see that in the young individual, you have this clean image of a lot of muscle in a 24-year-old. However, then if you compare that to a person in their middle of their 60s, you can see that there's a lot more of this fat. For one, there's less of this muscle, and what you'll also notice is that the entrenchment of this intramuscular fat, so fat that kind of gets in the way, gets between these muscle sections, is vastly increased in the older individual. So why is that important? Well, one of the reasons why that's important is because, well, the obvious, right? If you have less muscle and you have more fat, then you're going to have less strength, most likely. And of course, you're going to have a shrinking of the musculature. So why does that happen? Well, here we've got a cartoon image. So if I go back real quick, this image right here is represented here. And this image right here is represented here. So we've got our younger muscle, so the cross section. So here we've got individual cells that, again, we're looking down the cell. So we're not looking at it from the side. We're looking down the cell. So they look like tubes, like you're looking down a tube. So we've got these individual cells, and then we've got a little bit of this fat that's found inside, but it's not much. by comparison. So this cross-section looks healthy. However, when we look at a sarcopenic model, or looking at muscle cells, or muscle in general, muscle tissue made up of a series of cells, you still see the muscle cells, of course, but between these muscle cells, you see a considerable amount of not only intramuscular fat, but you also see fibrosis, which fibrosis is just connective tissue that ends up getting in the way. So the reason why it gets in the way is because typically you would want this to be filled with as many muscle cells as possible, but if that's not possible, the body ends up filling that with connective tissue. So why does that happen? Well, it happens because of chronic inflammation is one factor, because these immune cells will be activated and start to release a series of different pro-inflammatory molecules. Now, for a short period of time, that's perfectly fine, that's healthy, but if it's continuously occurring, this starts to create a lot of stress on the muscle cells. By these pro-inflammatory molecules will bind to the muscle cells and will lead to greater levels of a lot of the other issues that I'm going to be discussing later on. But one of those is greater cell death. So those muscle cells will eventually succumb and end up undergoing a process known as apoptosis, or in more serious instances, go under necrosis, which is a unregulated form of cell death. And then, because you experience this loss in these muscle cells, what ends up happening is it gets replaced by fibrotic tissue. So connective tissue, but in this instance, fibrotic tissue. And you have the proliferation, the production of more of these fibrosis cells or fibrotic cells, which are fibroblasts. And these fibroblasts will start to produce more of this tissue and deposit it between the muscle cells. So that leaves less room for the muscle cells. And on top of that, it clogs up that area so that you have, let's say, for the same amount of space, you have fewer muscle cells, which that then means most likely that you have less functionality from that same tissue. So if we go back to this image, right, let's say these are the exact same size overall, but if you start to look inside, you see that the muscle cells that make up the older muscle are far fewer than you would find in the healthy young individual. So that leads to reduced functionality in that regard, simply by the mere loss of the muscle cells themselves. Then, of course, there are issues that happen within the muscle cell and around the muscle cell. And this is actually a really cool phenomenon that occurs with aging. Not a positive phenomenon by any means, but it is detrimental, but it's still really cool. It's actually, I went for an interview at the University of Florida for their PhD program. And I interviewed with one of the researchers that actually does some of the high quality work on this particular phenomenon, just as a side story. And essentially what's happening here is that you've got a neuron, what's known as a motor unit. So a neuron, a nerve cell that is then controlling the muscle cell. So how do we move? Well, we move because our neurons are sending impulses, sending signals to our muscle cells to contract or to activate. And if we zoom into this particular endpoint of the neuron, so here's the body of the neuron, and then this is called the axon. And if we continue down here, we end up at the axon terminal. And then if we go a little bit beyond that, we have the connection to the muscle cell. So the neuron and the muscle cell actually never end up making contact with one another, but they get very close to one another. So this region right here is the muscle cell, and this is the neuron. So that if we just were to zoom into just this section right here. And so the neuron is never actually making contact, but it's constantly exchanging chemicals between the neuron and the muscle cell. And this exchange of chemicals tells the muscle to activate. It tells the muscle a series of different things. And ultimately, you want a healthy relationship between the two, where the neuron is constantly telling the muscle cell to activate or whenever it needs to. And the muscle cell is keeping the neuron happy by releasing different factors that keep the neuron in its location. So right outside of the muscle cell. Now, unfortunately, with aging, what happens is we have a process known as denervation, so denervation. And denervation is where the neuron starts to retract from the muscle cell. So I have a funny little video that I released a while back where I called this the divorce between the muscle cell and the neuron. So the muscle cell ends up chasing away the neuron by releasing some destructive factors, and then the neuron ends up retracting. So it moves away from the muscle cell. And in doing so, then by consequence, you don't have the signal anymore to activate the muscle cell. So even if, let's say, if we were to go back here, even if you were to look at a single muscle cell like this, even if it exists, the muscle cell is there, yes. But if the neuron isn't there to activate that muscle cell, the muscle cell is just going to sit there and it's going to atrophy very quickly. So it's going to shrink and shrink and shrink, and it's going to be essentially useless. So this is a really insidious and powerful way that sarcopenia, aging, affects the relationship and, well, certainly the relationship between the neuron and the muscle, but also affects the functionality of the musculature itself. So where mitochondria come into this a little bit is that we have two main populations. Some people debate a third, but there's two main populations of mitochondria in the muscle, or muscle cell specifically. So if we've got our muscle cell here, and if we were to zoom into the muscle cell here, we've got our sarcolemma, which is our cell membrane. So here's the outside of the muscle cell, here's the inside of the muscle cell. And we have mitochondria that are stationed, if you want to call it that, stationed in an area called the subsarcolemmal area. So the subsarcolemmal, meaning that, which is quite a mouthful, is found right under the cell membrane. So these mitochondria will generate energy and facilitate a bunch of other actions, but we're going to focus on energy. Will generate energy for any sort of functions that need to happen near the top of the muscle cell. And this is actually also a region right here. So this would be subsarcolemmal. So anytime that the neuron is going to activate the muscle cell, it needs significant amounts of energy to be able to do that within the muscle cell. So that's why we have these mitochondria. However, we also have a second population, or a major population of mitochondria that actually create a bit of a lattice work over the muscle, or inside the muscle, I suppose I should say. And they tend to be deeper within the muscle and tend to be closer to the myofibrillar areas of the muscle. What does that mean? Well, the myofibrillar areas of the muscle are the contraction units. So the ability for the actual mechanical ability for the muscle cell to contract is dependent on these proteins right here. So if we have these mitochondria around this area, you can imagine that this uses a tremendous amount of energy. That's why our metabolism is so high, because of muscle. And the contraction of that musculature on a day-to-day basis uses up mass amounts of energy. So we have this lattice structure of mitochondria. They're very close to this myofibrillar region, because they need to constantly be supplying energy so that the muscle cell can constantly be contracting. So we've got these two major populations. So from an energy standpoint, what happens with aging, what happens with sarcopenia, is that mitochondria will produce less cellular energy, known as ATP, or adenosine triphosphate. So adenosine triphosphate is another trigger for greater protein synthesis and reduced levels of protein degradation, which is, I've got simplified here. This is known as a proteasome. And this proteasome is part of the protein degradation machinery. So High levels of ATP, high levels of energy allow for more protein synthesis to occur, and low ATP or low cellular energy disallows protein synthesis as well as stimulates protein degradation. So with sarcopenia, we see more of this right here, where we see lower levels of ATP generation, and therefore we see an inhibition of protein synthesis, and we see increases in protein degradation. So that goes to this mechanism that I was talking about here, where it's not just amino acids, but it's also a reduced energy level within the cell from mitochondria. All right, so our midpoint conclusion. So sarcopenia is the age-related loss of muscle size and function with a strong emphasis, as I mentioned, on function. And it's caused by protein imbalance towards degradation. So we had the protein synthesis and the protein degradation, and it's focused towards degradation. Now, the mechanisms for that, I explained some of those throughout the talk up to this point. And reduced enzyme activity. So that's when I was talking about the reduced production of the glycolysis enzymes and the beta oxidation enzymes and things of that nature, as well as greater inflammation and fibrosis, which ends up dominating the muscle structure, so that the muscle cells, you have fewer muscle cells and you have more of that connective tissue as opposed to the muscle cells, which leads to reduced muscle functioning, which, as I mentioned, is the most important. And then intramuscular fat also starts to invade into that area, especially if you overconsume and if you're starting to gain weight, that intramuscular fat can also have an effect. So it's not just visceral in terms of your organs, it's not just subcutaneous under your skin, it's also starting to get within your musculature, which then it means that you have less room for the muscle cells. As well as this really interesting and really cool mechanism that I was talking about as well, where I was talking about my trip to Florida, where there's also this effect of denervation of the neurons, so the nerve cells on the muscle cells. The nerve cells will start to retract from the muscle cells for the reasons that I mentioned. And next, we're going to be covering how mitochondria actually cause sarcopenia. I covered one through energy, but there's other mechanisms as well. And how do we actually combat sarcopenia? So if you're interested in both of those topics and continuing this conversation, then certainly hop on over to my Physionic Insiders, where you'll get access to this study analysis and much, much more than just this study analysis. And with that, hopefully you learned something. There was a lot of information that I covered, and this is, again, all substantiated by 145 studies. So it's a lot of content. And I'll hope to speak with you in the near future. Have a good one. Bye.